Okay, listeners, get ready for a wild ride because this time on the deep dive, we're talking about a timeline that dwarfs even the longest history books. We're diving into the formation of planet Earth, from the Big Bang to the very ground we're standing on.
That's right. We're going deep, really deep, to uncover how scientists use things like uh, volcanic eruptions, earthquake waves, all those clues to understand what's happening thousands of kilometers beneath our feet. And get this, we'll even be exploring the evidence that continents actually move, kind of like pieces of a giant puzzle.
A geological jigsaw puzzle. You had me at geology. But let's rewind to the very beginning. Are you saying that every grain of sand, every mountain, even this microphone I'm speaking into, all came from a single point billions of years ago?
That's the mind-blowing part about the Big Bang Theory. Just imagine, if you can, all the matter in the entire universe squeezed into something smaller than, say, the period at the end of the sentence. Then, bam, expansion, cooling, and then gravity steps in, pulling matter together to form the first stars.
Okay, hold on. I got to let that sink in for a second. So you're saying those stunning nebulas, those swirling clouds of gas and dust you see in space photos, those are like giant stellar nurseries.
You got it. And here's what's even cooler. That leftover material, the stuff not used up in a star's formation, well, that can clump together to create planets. It's a process called accretion, and bear with me here. It's kind of like how dust bunnies form under your bed, except on a cosmic scale, where gravity's pulling these particles together to form planets, moons, the whole shebang.
So our solar system, Earth, we're made of star stuff. Now that's cooler than any science fiction movie. But I'm going to guess the early days of planet Earth, well, it wasn't all sunshine and roses, right?
You can say that again. Imagine a planet constantly bombarded by asteroids, right? The atmosphere's toxic, volcanoes are erupting left and right. Yeah, not exactly a place for a relaxing getaway.
Definitely not making it onto my vacation itinerary anytime soon. So how do we go from that molten mess to the Earth we know and, well, tolerate today?
Layers, my friend. It's all about layers. See, the intense heat from Earth's formation, combined with, all that radioactive decay happening inside the planet, it caused the heavier elements to sink towards the center. Kind of like, think about sediment settling at the bottom of a pond. The heavier stuff sinks, the lighter stuff stays on top.
Okay, so we've got the heavy hitters in the middle, but what about the thin layer we're all living on? How did Earth's crust, the solid ground, come to be?
So as those lighter materials rose to the surface, right, they eventually cooled and solidified, forming that thin, rocky crust, the Earth's outer skin, the ground we walk on. But here's where it gets really interesting. Sandwiched between the crust and the core is this mysterious layer called the mantle.
Okay, so Earth's core, Earth's crust, and in between, the mantle. But how do scientists study something buried thousands of kilometers underground? I mean, we can't just dig a hole and take a look.
You're telling me. It's not that simple. But scientists, they've got some pretty clever tricks up their sleeves. For one thing, they can study the stuff that gets spewed out of volcanoes, the magma. It's like the volcanoes are sending us messages from deep inside the Earth.
So every eruption is like a postcard from the mantle. Talk about express delivery.
Exactly. And then there are earthquakes. By studying the vibrations they make, those are seismic waves, they can actually map out the Earth's interior. Think of it like giving the planet a giant ultrasound.
So the Earth itself is like a giant science experiment. Pretty cool. But this idea that continents move, that's not exactly a new one, is it?
Nope, not new at all. You got to go back to the early 1900s to a scientist named Alfred Wegener. He was the one who really got people thinking about continental drift.
Wait a minute, wasn't he the guy who looked at a map and thought, those continents look like they could fit together?
That's the one. He noticed how, like, the coastlines of South America and Africa seemed to fit together, almost perfectly. And it wasn't just a visual thing. He actually found some hard evidence to back it up.
Like finding identical fossils on continents now separated by oceans? I remember learning about that in school.
Exactly. There's this reptile, Mesosaurus, lived millions of years ago, right? And they found its fossils in both South America and Africa, but nowhere else. Hard to imagine those creatures swimming across an entire ocean, don't you think?
It's like finding, I don't know, matching footprints on opposite sides of a freshly paved sidewalk. Something walked across when it was still one solid piece.
And the clues don't stop there. You've got matching mountain ranges, glacial deposits in the weirdest places. It all pointed toward a time when the continents were all huddled together, one giant supercontinent.
Okay, puzzle pieces, check. Matching fossils, check. Even our mountain ranges are lining up. So what force is strong enough to move entire continents around like that? It sounds like something out of a superhero movie.
That's the million-dollar question that stumped even Wiesner. He had the continental drift part right, but he couldn't quite figure out what made it all happen, the mechanism behind it.
So what was the missing piece of the puzzle? What did he miss?
Plate tectonics, my friend. This theory, it totally revolutionized how we see the Earth. Imagine this. The Earth's outer layer, it's not just one big solid shell, but it's broken up into these massive slabs of rock, and we call these slabs tectonic plates. And these plates, they're always on the move, bumping into each other, pulling apart, even sliding past one another.
You mean to tell me the continents are just hitching a ride on these massive moving plates? That's insane.
Hmm.
But if these plates are always interacting, what happens when they, collide? Things must get a little
Let's see.
messy. I think messy is putting it mildly. We're talking earthquakes that can level cities, volcanoes spewing molten rock, mountain ranges being built right before our eyes, geologically speaking, of course.
Yeah, messy might be an understatement. But you know what? It's those dramatic events that give us clues about how these tectonic plates interact. There are three main ways they do it: divergent, convergent, and transform.
Okay, hit me with it. Plate tectonics 101. Let's start with divergent. What's going on at those boundaries?
Picture two plates moving apart, like, say, ships sailing in opposite directions. Now, magma from deep down in the mantle, it sees its chance and rushes up to fill the gap, and that creates brand new crustal material. It's like the Earth's constantly healing itself, building new skin as it stretches.
So Earth's like a giant self-healing yoga master. That's one way to think about it. Where can we actually see this happening?
The Mid-Atlantic Ridge. It's this huge underwater mountain range where the North American and Eurasian plates are pulling apart. Because of that, the Atlantic Ocean gets a tiny bit wider every year.
Wow, you're blowing my mind here. So millions of years from now, the world map is going to look completely different. That's wild. Okay, so we got the plates pulling apart, but what happens when they crash head on, at those convergent boundaries?
Buckle up. When it's an oceanic plate going up against a continental plate, well, the oceanic plate, which is denser, gets forced down or subducted beneath that lighter continental plate.
Hold on, one plate gets swallowed up by the other. That's brutal.
It's a geological fight to the finish, and the oceanic plate, it always loses. You often find those really deep ocean trenches marking these subduction zones, and all that pressure from the plates rubbing against each other, that's where you get those massive earthquakes and volcanic eruptions.
Ah, so that explains why you have all those volcanoes along the Pacific Ring of Fire. That whole area is like a tectonic war zone.
You got it. Now, when you get two continental plates colliding, that's a whole other story. Imagine, like, two bulldozers, both equally powerful, going head to head. Neither plate wants to back down, so they buckle and fold, pushing up, up, up to form those massive mountain ranges.
No way. The Himalayas, those majestic peaks, they were formed by a continental plate crash.
You better believe it. And here's the kicker. That crash isn't over. That Indian plate is still moving, still pushing into the Eurasian plate, meaning the Himalayas. They're still growing today.
Those mountains are a work in progress. Okay, so we've got plates pulling apart, plates smashing together.
Yeah.
Any other way they can interact?
One more: transform boundaries. That's where plates slide horizontally past each other. Imagine trying to get a grip on something really slippery, like a watermelon, right? Lots of friction, lots of tension building up. Eventually, something's gotta give, and bam, earthquake.
The San Andreas Fault, right. That's the Pacific plate grinding up against the North American plate. Talk about living on the edge, literally.
Exactly. All that grinding is why California is always bracing for the next big one.
Wow, we've covered a lot of ground in this deep dive. We started with the Big Bang and ended up with the forces that continue to shape the Earth, quite literally, beneath our feet. We've seen how mountains are born, volcanoes erupt, earthquakes happen. It's pretty amazing when you think about it that all these powerful forces have been at work for billions of years.
And they'll continue for billions more. Continents will keep drifting, mountains will rise and fall, new oceans will be born. The Earth's a dynamic place, constantly changing and evolving.
It really makes you appreciate how something we think of as solid, unchanging, is actually always on the move. Definitely puts things in perspective.
It does, doesn't it?
Well, listeners, we've reached the end of our deep dive. We hope this journey through time and tectonics has given you a new appreciation for the very ground beneath your feet. Until next time, keep exploring and remember, it's a dynamic world out there.